here's the story of how it comes to be. Hello, I'm Brian Unger. I'm Professor Lou Bloomfield.
From the drawing board to the assembly line, it's how the ordinary is actually extraordinary. On some assembly required bounce houses, Zamboni, and windows. Well, we're in Burbank, California at the HQ of Magic Jump. Now, their motto is "We manufacture fun," which means they make these really cool inflatables, these jump houses. Now, you've probably driven by one of these like I have, gotten out of your car, walked into a children's birthday party and said, "Excuse me, kids, I need to jump in this." Yeah, it scares the children, but you got to admit it is a little fun. Sure, fun, but also curious, even to an old guy like me. What does it take to put the bounce in a bounce house? Since the beginning of time, kids have loved jumping up and down. But bounce houses, or jump houses as some call them, didn't get off the ground until the 1960s. Magic Jump is one of the giants of this industry, a family business run by Andy Bagumian. Why is it so popular now?
Because this is for kids, and the kids love to jump.
The Bagumians of Burbank. They opened in 1995 as a two-man operation. Today, over 30 people work to keep up with the high demand for buying and renting bounce houses.
We rent them like 80 jumpers a week.
Really? 80 jumpers a week?
Yeah.
Wow, they're going like hotcakes.
Yes.
The Bagumians make over 150 kinds of bounce houses, and they all start here with Manny Avedizian.
What we do is start with a concept. Say we want to start a giraffe.
And where do you get your ideas from, Manny? I mean, can you execute anything you want?
Of course. Yes, the possibilities are
You have
endless.
incredible confidence.
We start with a simple shape, like so. And I tell the program to flatten it out. Then I send that flat shape to the pattern cutter. And it cuts the exact shape that I've created here out there.
Out on the floor, we roll out the first 50 feet of vinyl for the pattern cutter. It's a computer-guided circular razor.
It's a really hard part. You have to just push the button. Yeah. I'll give you the sign and you just push this button.
Okay. Sam's going to give you the sign, and then I'm going to push the button. Waiting on you, Sam. Really? Good to go? Yeah. Let's make a giraffe. So what do we do now? Do we pick out these patterns?
Yes. Get these patterns.
So it really is like making cookies, and
Yeah, check it out. We have the beginnings of a giraffe.
upside down.
Upside down. Sure. Oh, yeah. Oh, right here. There you go. Wait a minute. Right side. Here's the eye. Yeah. This is turning into Wild Kingdom. Right here.
One of the biggest challenges of designing the first bounce house was finding a material that could withstand this.
Did you try to make a paper jump house? Did you make one out of glass?
No,
Did you make one out of latex? You did. I was going to say latex is inflatable, stretchable. You can bounce on it.
It's not very durable.
That's right. It can break.
Turns out plastic is perfect for a bounce house, but not just any plastic will do. The best kind is vinyl, and the Bagumians get theirs from up north.
The Nazil Corporation here in Ontario, Canada, makes about 1,200 miles of vinyl every year. You know how much vinyl that is, Lou?
Tell me.
That's enough to build a freeway from Los Angeles to Houston
made entirely of vinyl.
I mean, one big slip and slide.
Oh, indeed. A lot of vinyl. Whipping up a big pot of vinyl is like cooking with, well, big pots. We start with plasticizer. This is the stuff that gives plastic strength and flexibility.
Now, Lou, I see all kinds of top shelf plasticizers here. They all have weird names. Plastistab, plasticizer, Plastimol, DOA. That sounds good for you. This all gets whipped up into some sort of cocktail? How do you know?
Yeah, well, we're starting off with the liquid basis for the plastic. The plasticizer are like molecular lubricants. Polyvinyl chloride, or PVC, is a hard, brittle plastic. This stuff softens it. Are you ready for it?
Yeah. Oh. Now, how much vinegar do we add to this?
Now it looks like fake butter for popcorn. The next element we add to our chemical stew is color. Since we're making bounce houses that must be eye-catching to little kids, we need custom colors, lots of them.
Oh, thanks, I needed that.
Now we have to add the final and most important ingredient, vinyl, or PVC.
This is polyvinyl chloride, a hard, brittle plastic consisting of lots of little chain-like molecules, all tangled up and barely able to move relative to one another. It's kind of like spaghetti you left in the bowl overnight with no sauce. But once you mix it with the plasticizers in the vat, they'll lubricate those molecules, kind of like adding sauce to the spaghetti. And now you have a flexible, tough, elastic material to cover the fabric for Moonbounce.
The liquid vinyl will be poured onto a polyester fabric and then put into the oven.
Now it'll travel about 20 meters at 400 degrees Fahrenheit and emerge here, perfectly cured. It's then fed to this final spool right over here where it's a completed product of vinyl and it's ready to be shipped to, say, Magic Jump to make a beautiful new bounce house.
We're assembling a bounce house. This is an air-cushioned jumping heaven for kids. All made possible through PVC, or vinyl. The airtight yet flexible material is perfect for helping kids defy gravity. They call it fun. At Magic Jump in California, they use about 3 million feet of thread in a single year and 35 tons of vinyl every month to make bounce houses. Like the one Manny Abadizian here is making, it's shaped like a giraffe. Ah, but what is a giraffe without its spots? This calls for some heavy-duty glue.
And then any kind of special glue in here? Or
Yes, this is special vinyl cement. It's not that toxic where it will give you brain damage. Or,
Won't give you any brain damage?
No.
Won't do any of that?
No.
I shouldn't sniff this, though, basically.
No, it's not good to sniff it, yeah.
Okay. Let's see him making a model airplane.
Yeah.
So basically, Manny, our computer designer inside, has created what we will call spots for our giraffe. And this is the part that gets actually physically kind of messy. See, Manny, he gets to sit at the computer
Exactly.
and just peck away at the keyboard. This is where the actual labor comes in. I'm starting to feel it already. Yeah. It's not exactly like a rose garden. No. It's pretty, woo!
That's why the guys that do regularly are not here today.
Yeah. Oh, they're not? They're recuperating? Okay. Good. I'm ready for the long haul. Are you?
Yes.
Okay.
Go ahead.
Here we go. Like so?
One done?
One done. And how many? 149 to go.
Yeah.
Manny, we should be more economical with the spots, right?
Yes, you should.
Now, vinyl is tough, even airtight, but bounce houses, they need to breathe and not hold air in like a balloon. If that were the case, too many kids in a bounce house would just blow the sides right out.
So this thing adapts, and it has to be allowed to adapt to the number of people inside. And the way they do that is with the air compressor that fills it. This unit puts air in to blow it up and to keep it inflated against the leaking
but it also allows air to come out when the house is carrying a lot of weight.
It's like the biggest sewing job in the world. I mean, wow. I got a little gas pedal down here. So, do you want to get on the other side and pull it through for me? Okay. I mean, ordinarily, do you have someone who helps you pull all this material through? So it's like a two-man job?
Yeah. Because you cannot do it by yourself.
Yeah, but you did want to see me try to do it by myself, didn't you? Hey, do you like working for Sam?
He's my cousin, so yeah.
He's your cousin? So you gotta... I don't think he knows what he's talking about.
You want to see the difference?
You want to see the difference?
Yeah, right here.
Between what you sewed and what I sewed? Oh, jeez. I'm just going to say that you did this whole thing because this is where you were awake, and then this is where you fell asleep.
Drunk.
Right
Drunk.
here. Oh, darn. Break time. Now, while I've been trying to sew the head of this giraffe, the rest of the crew is assembling the body. 170 square yards of vinyl, all fed through industrial-grade sewing machines by hand. This heavy-duty needle is pretty scary. Sam, how long does it take to pass an entire bounce house through one sewing machine like this?
A unit this size takes about 2 days.
2 days. So John will be working for 2 days just sewing one bounce house?
Yeah.
Imagine, John, this thing could just take your finger right off if you slipped. If you notice it, John actually has all of his fingers. Our bounce house is done. 200 pounds of vinyl, cut, sewn, and glued. The moment of truth. Time now for an awkward moment with Sam Agumian. Kick off the shoes, dude. It's time to bounce. You know what I'm saying? Is the bounce still any good? Yeah? Like enough? Yeah? Sam, you're not jumping high enough. If your head touches this, if my head touches this, pass the test. Can I pull this down though? No. Oh no. I can't do that? Thanks for letting us spend the day with you. Thank you. It's a nice house. I made it. I'm exhausted. It is one of the world's great mysteries how one sweep of this cool ride turns rough, dull ice smooth and shiny. Now, you've seen it over and over ever since you were a kid, and you still don't know how it's done. So, how do you take a dirty, grungy ice surface like this one and turn it into a nice, glassy, silky, smooth one like this just using a razor blade, a few gallons of water, and do it in just seconds? We are inside the Zamboni factory in Paramount, California. Now, Zamboni is a name that is synonymous with ice resurfacing. And anyone who has been to an ice rink has had to wonder, how do these ice resurfacers work? It's kind of a mystery. Well, not really. I mean, it begins with a vehicle designed to drive on ice. Now, just like any other set of heavy-duty wheels, the Zamboni ice resurfacer is built on a heavy-duty chassis with enough steel to hold 5 tons of ice and water. So we are building our chassis that is going to hold the tremendous weight. How many pieces of metal make up this chassis, Perry?
There's about 23 pieces.
About 23?
Yeah.
Enough to build a very strong chassis. When Frank Zamboni built his early versions of an ice resurfacer, he started out using a Jeep chassis, but it couldn't handle the weight he needed to put on it. Now, Frank, who was a real avid tinkerer and a one-time mechanic, decided to build a chassis from scratch. The biggest change Frank made was these reinforcement beams that span the width of the chassis.
Now they weld each seam by hand here. That kind of expert detail is what makes a Zamboni ice resurfacer last up to 50 years.
That's good. Don't want to mess it up too much.
Well, Patrick here is raising this giant steel frame that we've welded. It's got an anti-corrosive coating, which will help us make the big rusted.
The folks at Zamboni have a ginormous 85% global market share in ice resurfacing, yet it's still very much a mom-and-pop operation.
I think it's really a bit of a homegrown company here. We work the same way that Frank Zamboni originally did, where he saw a problem and he would fix it.
Yeah, because this assembly is a little, I mean, it's personalized.
Right. We've got Zamboni and our Zamboni notes.
I'm on break.
Our chassis is built and wired. Now we need some power. This compact, maneuverable machine, it does a lot of work in a confined space in a short amount of time. And to handle all that, they use hydraulics.
Well, what do you try to lift? A couple thousand pounds of ice and snow and water. How you can do that with just a motor? You're going to need some pretty serious gears. Okay. So they use hydraulics for that.
In hydraulic systems, power is distributed by pushing fluid from one place to the next. In the Zamboni machine, an engine or motor powers a pump that forces pressurized fluid through hoses that feed into all the parts that rotate or require heavy lifting.
It can push with 10,000 pounds of force. It can lift something that's as heavy as like a bus.
Really? That hydraulic system is key to handling the Zamboni's three main jobs: removing, cleaning, and smoothing over the ice. And none of that can happen without some very big tanks.
Are you ready, Jose? Thank goodness for this hoist, huh?
Yep.
This is about a ton.
This.
Yeah. Do you want to, let's just lift it.
Let's
ourselves.
lift it.
No, lift it to knees. Okay, ready? Yeah. All right, let's use the hoist.
Thanks to hydraulics, this snow tank can hold, lift, and dump 100 cubic feet of dirty ice.
I want to lower this down. And this looks like a hydraulic
Cylinder, which actually lifts the tank, tilts it forward so the snow will come out.
Our Zamboni can now carry the dirty ice as it gets shaved away, but it still has to clean the ice and smooth it out. To accomplish this, the Zamboni needs to carry a lot of water on board in tanks.
This is the world's worst hot tub.
There are three tanks on the Zamboni. There's the snow tank, which holds the dirty ice after it's shaved, and the freshwater tank, which holds the water that cleans the ice. This machine is like a big bar cart.
Now, inside this tank goes vodka. And what they do is they lay this vodka down on the ice and make a nice big martini. Have you tried licking the ice? Try it sometime. Get a buzz.
Okay, maybe not vodka. This tank actually holds the fresh water that pours out onto the ice. It freezes over and becomes new ice.
Hello, Bloomfield. You forgot your flip-flops. Once these Zamboni ice resurfacers are assembled, they often bring them out here to the mean streets of Paramount, California to see what they can do. That's Richard Zamboni behind me, tearing it up. How's she handling, Richard?
Very good.
Good?
Getting in there, good circle.
Richard Zamboni is Frank's son, and he still runs the company in the same way and in the same location, sunny, snowless Southern California.
Mr. Zamboni, let me ask you a question. This is not a completed assembly, obviously. We've got things still to do here. But why do you bring them out here? What are you looking for?
Well, it just depends on what shows up. Through assembly, one thing shows this, you want to be certain before it goes out the door.
What else does this need?
Well, this one will have the paneling going on it, both the sides, the front, and the back. and then the conditioner
Down
machine,
in
which
here,
goes
right?
down there, the working part of the machine, and eventually go out the door.
Our Zamboni ice resurfacer has its customized 6-cylinder engine on its custom-built chassis, and it has its tanks to hold the ice and water, but it's not yet equipped to clean the ice.
Hi, I'm Brian Chapstick.
Back in the 1950s, cleaning the ice was a big problem for Frank Zamboni. At the Zamboni family rink, a tractor would pull an ice scraper around, then 3 or 4 workers cleaned and smoothed the ice by hand. This process took more than an hour each time.
Okay, now we're going up.
And it's going that way?
Yes, sir.
Right towards that camera?
Right towards that camera.
Don't get hurt, Fred. Frank Zamboni wanted to turn dirty rough ice into clean smooth ice quickly. He set out to invent a brand new machine that would revolutionize ice resurfacing and keep his customers skating. So he created what's known as the conditioner. It clears, cleans, and smooths over the ice almost instantly. The first trick is to make the rough ice disappear, but it has to go from the back of the machine where it gets collected to the front.
So this is the underbelly of the conditioner, minus the blade. The blade mounts right here on the blade holder, what they call the T-bar.
The blade is 57 pounds of razor-sharp, high-carbon steel, tipped 15 degrees up from the ice to form a ramp that lifts the shavings up and into the auger. The auger is another kind of ramp, only the blade wraps around a center beam, forming a screw. And as the screw moves around, so does the ice. This auger is basically a spiral ramp that pushes the ice toward the center. See it going? Right, the other side is also pushing it toward the center.
All moving toward the center, and then this little guy right here, I presume, is feeding it to the vertical auger.
Yes, this is the horizontal auger. There's a second one we don't see yet. Vertical carries it off to the ice bin.
Pretty cool, because this is the part hockey fans don't get to see.
Our blade and auger have cleared off the dirty ice, but we still need to clean and smooth it over. And we need to do it without having to make another pass on the rink. This part of the conditioner is actually a highly engineered plumbing scheme. Water is piped into the conditioner, which washes the ice.
This is the water pump that actually sucks up the water that gets built up underneath the conditioner.
Another pipe at the rear of the conditioner delivers fresh water to form the new ice.
It's actually sprays onto the back end of the conditioner, which flows down, and the towel actually spreads it out real smooth.
We are almost done assembling our Zamboni ice resurfacer. The engine, control panel, and hydraulics all installed.
So heavy.
Whether it's electric or gas-powered, each ice resurfacer is assembled by hand.
You do this by yourself?
Before we take this baby out onto the ice, we need to ready our tires for the slippery ride. Old snow tires won't do. This massive machine has to turn on a dime, on ice, so we need more than just traction. We need bite.
Perfect.
Nice.
So Brian's putting studs in the tire. These are tungsten carbide studs. A stud made of carbide is incredibly strong and hard, and will stay sharp on ice, essentially forever. When the Zamboni goes over the ice, they grip the surface like little teeth.
Yeah, I mean, you get some serious grippage here.
Perfect. Man, you're pro. Second job, and you're perfect.
Thing is just hauling.
You know, 8 miles per hour never felt so good.
And now I get a lesson of a lifetime. Richard Zamboni has agreed to teach me how to drive a Zamboni. You never know when this is going to come in handy.
Tell me exactly where you're looking when you're driving. Are you looking ahead? Are you looking down at where the
most of the action is occurring down here with the auger, or where are your eyes?
Once you get going, you're actually interested in getting your process going, the different steps.
Okay.
Lower the conditioner, set your blade, get your conveyors going. And you're looking forward at that time. And then you're doing your pattern, you want to be sure that your alignment is such, you'll overlap a little bit, but not too much, so you get on and get off the ice without too many laps.
So it's kind of a forward, down, back, forward, down, back.
Very true.
It sounds very difficult. And you're juggling a lot.
You are, but it takes a little while, and the really good operators can get out there and they just make the machine talk. There's no question about that. But they know what they're doing, they're watching it, and it becomes very simple after you've gotten the hang of it.
Simple? Not quite, but fun? Yes.
I'm lowering the blade a little bit here, so we just kind of see how the shape's going. Good. So we're in really good shape now and ready to start the water operation.
Okay.
So we'll just open this now, maybe about halfway.
Stay on. Where would my right, left wheel be on?
Your left will be on that edge there, the separation.
I'm ready for the guards.
You want to anticipate your turn down here. A little bit more down.
So I'm going to go that narrow lap.
That's right.
It is trickier than you think. It's a little bit of a juggling act, right?
It is, and you got a lot of things to concentrate on, Brian. Because when you leave spots along the ice, people see that and they think, I can do a better job than that guy can.
Yeah, because you do have to go back and hit patches it left behind.
An accomplished operator doesn't have to do much going back, though. And that's the thing. Maybe as you're getting on the thing a little bit more, you'll miss something. But I noticed a couple of spots you missed.
You're being kind. If you had to assign me a grade, Richard, what would you give me?
Well, I think it's a strong C.
Oh, man, a C! And you're being generous, aren't you? Thank you so much. You know, it's such a simple, routine act of everyday life, opening and closing a window.
Yet I'm not really sure how or why this window glass started out as a heap of sand. So how do you go from sand to a perfectly clear window?
Are you still here? The story of windows starts here, way up here, 60 feet off the ground in Carlisle, Pennsylvania at PPG. These are giant, massive silos that hold the key ingredients to glass.
The main one, sand. Every day, 800 tons of it are fed into the building here, and then mixed with two elements critical to the manufacture of window glass. Soda ash and lime, or sodium carbonate and calcium carbonate. They lower the melting point of silica sand and alter its basic molecular structure.
These chemicals soften the glass. They make it easier to melt. They terminate the silicon-oxygen chains. They make a more manageable glass to work with. And that soda, lime, silica glass lies at the heart of every window.
Now, all of our raw materials have been mixed together and dumped into tanks like these, where it's a cool, low 3,000 degrees. It's actually hotter than molten lava. And it will take 3 days for a single molecule of sand to get from this point all the way to the other end of the factory, where it actually starts to resemble a sheet of glass. All right, so we're wearing this protective garment for a reason, right?
Right. Wearing Kevlar gloves, fire retardant.
We're dressed like big oven mitts.
Right.
Yeah, it's pretty hot where we are, but it's going to get a lot hotter inside, right?
Yep.
So let's rake.
Steve Anderson and I have to rake this batch quickly. Goal? Well, don't let the rake melt first, and spread out the mix to reduce air pockets that might form.
Pull that whole raft over to the wall.
Yeah, it's like tapping.
Yeah, it's just like that.
It doesn't take long for the batch to start looking less like sand and more like an overflowing volcano. The only way to see this river of glass is through these polarized metal masks. Without them, your vision will be, well, gone.
There, inside that shiny surface on the bottom, that is liquid glass. For 10 hours, the molten mix is superheated behind thick walls to allow gas to bubble up and out. Bubbles drive glass makers nuts. After all, nobody wants to look out a window you can't see through. There is only one way to create plate glass without bubbles, and more importantly, flat on both sides.
If a window isn't flat, it'll distort your vision, like a wrong pair of glasses. But making flat window panes is hard, and it used to be done by blowing giant glass bubbles, cutting them open, and laying them flat before they solidified. But they didn't end up perfectly flat. So since 1959, glass has been made by pouring molten glass on a river of liquid tin.
The surface of any vast, undisturbed liquid is flawlessly flat. Tin ingots are melted down, creating that perfectly flat surface. The glass pours onto the tin and immediately begins to cool.
Tin and glass don't mix. Like oil and water, the lighter glass floats on the denser tin. And the result is a system where the liquid glass and liquid tin start at high temperature one end of this giant river, and they cool. They're cooled deliberately until at the end, the tin's still liquid, but the glass is solidified.
Compared to glass, tin's melting point is low. By the time it reaches this stage of the assembly, the glass hardens, floating on top of the molten tin like driftwood on water. Still very hot, as in 1,000 degrees Fahrenheit hot. The glass moves down the line in one long continuous sheet. It stretches 1/4 of a mile, and because of its length and temperature, it's surprisingly elastic and strong enough to really beat on.
This glass pumps as hard as you want. You won't break that glass. It's extremely strong in its first
Steve, I think you've actually proved your point there. So from here to there, you need to bring it down about 100 degrees.
100 degrees, and that's why we have such a long cooling conveyor, is to allow it just to cool down naturally.
A robot then cuts this long ribbon of glass into slabs that run about 12 feet across.
These long pieces of glass have been cut, and in a moment they'll be packaged and then shipped to their distributors, where they'll be turned into windows.
To make windows, we haul glass down the road a ways to a window factory called Winco in Morgantown, Pennsylvania, where on average 400 sheets of plate glass stream in all day, destined to become window panes. Working with this stuff can be very dangerous.
Now this is kind of like Kevlar?
Yeah, this is Kevlar material.
This is the same stuff they use in bulletproof vests.
Yep. When you're pulling them off the table, you pretty much, that glass is right at your waist, right at your leg area, so we want to make sure that's protected.
Always put your Kevlar sleeves on first. Andy, dare I ask, has anyone ever been cut?
Yes.
Good. I had no idea that Dickie was making a comeback. Lou, suit up, my friend. You got to put it on. So you got your Dickie on, you got your Kevlar sleeves, and you really are kind of ready for a kind of a Liberace thing in Vegas. It's nice, with a little Michael Jackson.
At the window factory in Pennsylvania, we've got these huge plates of glass that need to be cut into window panes, or lights as they call them. They're floating on what appears to be a giant air hockey table, which makes it easier to move them around.
Now I notice you don't treat these pieces of glass with kid gloves. You really just kind of throw them around.
Yes. Yeah.
How big is this glass, Andy, right here?
That's 7284.
So one hand moves this basically over this table. There's so much air shooting up to the surface.
Yes.
Now, cutting glass is far different than, say, cutting wood. You just need to scratch the surface, literally.
Glass breaks by tearing. When you stress it, it finds a defect in the surface and tears through from that point. And if you don't
put defects in yourself. It's going to tear wherever the heck it likes. They introduce defects all over the surface in a pattern that controls the tear. So Andy, how many will we cut here?
This particular pattern will probably cut about 15, 17 lights.
So you can really move at a good clip through here.
Yes.
And now it's time to break it out. Is that right?
Time to break it out.
So I know that the scoring line, I can see it right here.
Yep, perfect.
That was pretty easy.
As soon as you get that glass up in the air a little bit, that brake's going to shoot all the way through the score.
Break it, you bought it. Beautiful. Another scoring line right here. Okay. Now, check this out. See that little piece right there?
Yeah, that's the only thing when you're...
Did I break that?
So a lot of the glass tends to slide a little bit.
Yeah.
So when they break it, they want to make sure they keep a handle on it so it doesn't slide into each other.
And I also chipped this.
Yes, we would actually reject both lights and recut them.
So I basically broke 2 pieces of glass the first time I tried to cut them.
Yes.
I've costed the company how much money?
Thousands.
Thousands of dollars? We should just pack it up and go home.
Unusable panes, like the ones I specialize in, are recycled.
Go ahead, take a step towards it and toss it in.
Cool.
Perfect.
Typically, these guys kick out 9 panes or lights every minute. That's 3,000 a day. From here, the panes roll down the line to be framed by the components that add up to a window.
Hold it over here. Well, that was pretty simple. Hold it corner. Hey. Almost got it.
Manuel Cuevas and I are making aluminum spacers for energy-efficient windows.
There you go. Okay.
Now our spacers are fit between 2 panes.
And while we're putting this first pane of glass and the spacer on top, right behind me, the other pane of glass that's going to be its mate will be joined with it on that big giant press down there. And eventually go through the heating process where the adhesive, the sealant on the edges of these spacers will sort of melt a little bit and seal it up permanently. I actually sound like I know what I'm talking about.
At this point, some of the panes will be fed onto a line dedicated to making hurricane glass. The windows that can stand up to the fiercest winds. These amazingly strong windows rely on one key material.
This is the substance that goes between the 2 pieces of glass. This is the magic of hurricane glass.
Yeah.
Now, Lou, what is PVB exactly?
Polyvinyl butyrol. It's a tough, clingy plastic that'll grip onto the glass snugly, and it'll be very hard to get through even after the glass breaks.
The PVB is positioned between 2 regular panes of glass. This PVB sandwich can withstand almost anything thrown at it by a hurricane, even a tornado. We're going to prove it in a moment.
Kind of went over a little, but
Yeah, we're amateurs anyhow.
boy, that's an understatement. What's that? Time to cut?
Time to cut.
Now, Lou, we have to heat this. Now, how does that work? I mean, what is it, like an oven?
Well, we're going to go first into a 1100 degree Fahrenheit oven, which will only heat the glass and plastic to about 180 Fahrenheit. That's enough to get the PVB tacky and stick the whole sandwich together forever.
Good.
But then it's going to go into an autoclave, which will bake it under high pressure for about 3.5 hours. Really melt the plastic, about 280 degrees Fahrenheit, and you'll end up with a permanently bonded, totally clear assembly.
But that's the finished product right there.
Yeah, this is after it comes out of the oven, literally.
Yeah. I mean, after the autoclave, clear as a bell.
It looks exactly like any normal glass.
Now we'll put it to the test.
So we are in the R&D department of Winco, and it's time now to put our hurricane glass to the test. We've made it, and this laser is actually pointing at our window that we just made. We're at looking at our WMD here. They have it by Winco, and this is basically a giant air cannon that's going to shoot this projectile out of this barrel to simulate a 160 mile per hour hurricane wind. So you have your little musket loader there, and you're going to stuff that in. And we're going to see how much this glass actually can withstand. 50, what, per second?
Feet per second.
50 feet per second. Are you ready to fire this baby?
Oh, yeah.
So there is a procedure to follow.
Okay.
Plug up. I'm going to pressure, enable.
Safety first.
Fill mode. Check this out! I mean, it really does hold.
The layer of PVB between the pieces of glass is so tough the board goes from a speed of 50 feet per second to a dead stop. It actually bounces back toward us.
Well, what did we break?
We
broke the outside layer of glass, which is totally normal.
Okay.
And then the inner composite, we broke both sheets of glass. But that plastic layer is unbreakable. And that's what we're dealing with now. We're not kicking against it. It's a trampoline. You can't get through this stuff.
So it's an elastic window.
Right.
Whether these panes are keeping out the wind or your noisy neighbors, they all funnel back onto the main assembly line to be turned into actual windows. Making windows, a process that once took 3 weeks, through automation, now takes just 72 hours. Frames, sills, and sashes are heat welded together. This last stage looks like a race car pit crew. In the span of a few seconds, screws, glue, and locks fly onto the windows.
So this is the window that we put together earlier, completely sealed, drops into the sash with the adhesive, and voila, there is the window.
We try to average about 40 windows per hour on this line.
Yeah, not today.
The top window is fastened into place, glazing pops on, the sash slides in.
Well, you gotta really move that thing, huh?
And that's a wrap.
What took 21 days is now a 3-day process with this super modern, efficient assembly.
And only a week before that, the glass, which is to keep us sand.
A pile of sand, superheated, liquefied, cooled to a quarter-mile ribbon of pristine plate glass, scored and snapped, fortified and framed.